Good day. Thank you for the opportunity to discuss the pitfalls of sampling for gold in process plants. My name is Willem Slabbert. So, gold sampling can be presented with a 3-day course, and some sampling gurus of the world might still believe that that is inadequate. However, today we've got limited time, so I've selected the following content for the presentation today. First of all, we need to understand the intent of sampling for gold. Then the challenges of sampling within a process plant for gold. This presentation would exclude any form of geological sampling and only focus on metallurgical sampling within the process plant. We'll hear some statements from the sampling gurus about the challenges of sampling for gold. Then we'll look at typical bias generating devices. In other words, what can you do wrong versus sampling from one-dimensional streams that turns heterogeneity guesswork into measurement. We'll then go on to ask how much sample do we need, what the heuristics are for practical sampling, and we'll conclude with some pitfalls for gold sampling on both slurry and dry sampling applications. So the purpose of any sampling, and particularly important for precious metal sampling, is to have a sample that is accurate. We know that somewhere within our process stream, we must have an actual value of what the grade of that stream is, whether it is a tail stream, a concentrate, or a feed stream. Now, the problem is that we do not know the actual grade. Technology has not developed where we can have a device or even an analyzer that can look inside the stream and exactly tell us how much gold is in the process. We therefore have to sample the stream that it is represented in every way by that sample increment or composite sample to tell us what the grades and the properties of those streams are. In other words, when we want to take a sample, we must undertake to take an accurate sample. The average or mean of our sample increments must therefore correspond to the actual value in the stream. If that doesn't happen and there's a difference in accuracy, as shown by this arrow, our sample can be said to be biased. So a bias is a deviation in accuracy. The second criteria that we want to meet is that we want to have a good precision level. If we measure a stream at a certain instance in time and we repeat that measurement 10 times, we want to get a very narrow distribution of the analytical result. In other words, our result must be reproducible. If not, we would not have a lot of confidence in our result after all. So these two undertakings, having both accurate and precise samples, can only be achieved when all the constituents of the lot to be sampled are given equal probability P of being selected and preserved as part of the sample, which leads to the notion of equiprobabilistic sampling, which in turn leads to the notion of correct sampling systems. So correct, the word in this instance means there is nothing shortcoming in terms of accuracy or precision. So with this very basic statement, how come then is sampling, and sampling in particularly gold, such a big problem then? We know what we want. We want an analytical result that reflects the actual value in our stream in terms of grade and precision. But the question is, what do we need and what are the risks? So some of the risks and challenges of sampling for gold are over the years listed by some of the foremost sampling gurus in the world. I've selected some of their references here. Gold is difficult to sample because it has a very high heterogeneity. Now, this heterogeneity is emphasized when grades are decreased. In other words, if we were lucky enough to have a gold mine where the grades runs between 20 and 22 grams per ton, the relative variability, 22 minus 2, is only 2 grams per ton. However, if we make that variability relative by saying 2 grams per ton variability over an average grade of 20, then the relative variability is only 10%. However, if we mine in other parts of the world where the grade fluctuates between 2 and 4 grams per ton, we have the same difference in grade being 2 grams per ton. However, then the relative variability, because the grades are low, changes from 10% to 100%. In other words, the heterogeneity is amplified at low grades. Another typical problem with gold sampling is the density of the gold metal, which clocks in at 19.3 specific gravity. So gold is prone to segregate over and above the heterogeneity that we might experience within the geology. So quite often, because of these characteristics, sampling gurus conclude if something can go wrong in sampling, it will happen on gold sampling, and it will happen in a very big way. Cross-stream sampling is non-negotiable and will be discussed in the next slides. We may be prompted to say that if we have a bias in our sampling, in other words, the gold produced is not equal to the gold measured, we're consistently producing more gold than what we measure coming into the plant and the feed stream, we may be prompted to apply a correction factor to that number if we see a consistency in the difference between gold produced and gold fed. However, a lot of these sampling gurus have proven that a bias is never constant, and quite quickly our metal accounting can go to the assumption of metal accounting, which does not ever always happen. Sampling is not gambling, and today's presentation will tell you how to take the guesswork out of sampling and turn it into measurement. For an effective sampling protocol, in other words, how much sample do we need, how often do we need to take sample increments, and how do we need to analyze for the gold at our specific operation, you often need expensive and tedious heterogeneity tests. The theory of sampling, written by Pierre G, lists the fundamental error equation of sampling that tells us how sample mass is related to sample precision and also the parameters that affects those two balancing inputs. Lowest cost procurement is not a route to quality. We should all agree that there is a lot of heterogeneity in mineral processing streams. Now here I'm not talking about gold grade heterogeneity from a mine to a mill. Here we're only talking about typical mineral processing equipment like slurry flowing in a pipeline and conveyor belts and stockpiles. We can see from the slide in the top left hand that slurry flowing around a pipe bend has different velocities and therefore different carrying capacities that will quickly result in segregation of gold to the zones where only the highest carrying capacity exists, while some of our inert silicate type materials might transpose to the outward of the pipe bed. In other words, there is severe segregation in slurry pipelines given different velocities in different parts of the pipe. On conveyor belt systems on the top right-hand slide, we can see that fines will typically sift through the material burden onto the top of the conveyor belt, with distinct zones then of lumpy and fines mixed materials on the shoulders of the conveyor belt and almost selectively coarse material at the top of the conveyor. This effect, however, goes further. In the bottom right-hand corner slide, when the segregated material is presented to the head pulley, the radius of rotation of the coarse material typically allows the momentum and inertia of the material for the coarse material to travel further, while the fines are falling almost vertically straight down. Now, if we were to construct a stockpile using such a conveyor system, as indicated by the diagram in the left-hand corner, bottom, we would note that the coarse material would almost selectively report to one side of the stockpile and the fines to the other. So we can conclude that the grade across the stockpile distribution would also be heterogeneous. But it even goes further. If we zoom into the wall of the stockpile, we can see that due to wind and rain, the fines would again propagate into the stockpile, while the lumpy material only remains on the outer edges of the stockpile. So variability and heterogeneity of material within the mining operation is a given, and I have yet to come across any perfectly mixed streams, particularly in gold applications. Next up, we look at bias-generating sampling devices. The first device we will discuss is called a poppet sampler, in parts of the world also referred to as a thief sampler. This device consists of a typical valve actuator with a piston-type plunger that moves into the slurry stream to extract a small sample volume that then reports to a composite sample bucket. On the bottom diagram, we can typically see the valve actuator, the working mechanism, an isolation valve, and then the installation of this equipment onto the side of a pipe. However, we can quickly agree that the installation position, and with the plunger only measuring a short distance into the slurry flow on the inside wall of the pipe, the installation position would then determine which part of the flow we selectively extract. If we were to install 4 poppet samplers around a pipe bend as indicated on the left, first of all, none of those 4 samples would measure the entire flow stream. And with the segregation of particle size distribution and density, each 4 of these poppet samplers would give us a different result. The conclusion is that this device would typically be inaccurate because it doesn't measure the true grade of the stream, and also not reproducible, so our sampling precision result is also affected. In our next system, we tone things down and present it in a really simple fashion to illustrate some of the principles of bias generation. Now, in this system, we have some gold ore pumped in a pipeline. The grade of the ore consists of 4 gold particles relative to 24 inert particles, and in total we have 28 particles filling the lower half of this slurry pipeline, with the top half essentially being water. So the gold grade is then 4 over 28 particles, which amount to 14%. When we sample this stream with a poppet sampler mounted in 4 different positions identified by the installation team, we can see that the first sample would produce almost only water with no solids. Samples 2 and 4 would produce samples with only inert material and no gold. And unfortunately, sample number 3, if this was a tailings line, would produce pure gold. In other words, this inconsistency is guesswork. And if you recall, the sampling gurus say that sampling does not need to be gambling. If we improve on this system and we use another automated mechanical sampler called a shark fin sampler, we could then sample the entire flow stream from top to bottom as indicated with the rectangle on the right. The sample we extract would then consist of 1 gold particle relative to 4 inert particles. In other words, the measured grade is equal to 1 over a total of 5, which is 20%. But remember that the true gold grade was 4 over 28, only 14%. This sample bias or inaccuracy means that the true grade of 14% is now being represented by a bias sampler as being 20%. So clearly, we have an accuracy problem with this type of sample generating device. So now that we know what not to do, it becomes evident that if we want to measure the variability of a stream, we must sample across the whole width and height of that stream in order to account the proportion of gold versus inert material, or in other words, your particle size distribution with equal probability. That means we have to use cross-stream samplers. Now, cross-stream samplers works in a way that we measure the heterogeneity across 2 of the dimensions, and instead of having 3-dimensional variability, because we eliminate and measure 2 of those variabilities, we are then only left with a variability over time or along the length of our conveyor of how much the grade varies in that instance. So here are some typical examples of how to take 1-dimensional cross-stream samples. First up is a cross-belt or hammer sampler, where a sample cutter is actuated to cut across the full width of the stream, and the height of the sample cutter also allows the full material burden on the conveyor belt to be sampled. Also, for dry systems, we can use a belt end crosscut sampler. Now, a belt end crosscut sampler would sample from the head pulley of a conveyor and would sample across the full stream width. And again, the height of the cutter will allow us to sample also the full burden height of the material that was traveling on the conveyor. Moving over to slurry systems. For vertical free-falling slurry systems, a radial type of sampler called a 2-in-1 sampler can be used to slurry the full width and breadth of a slurry stream. For horizontal flows, a Launder crosscut type sampler can be used to again sample the full width and height of a slurry stream, measuring the variability that may exist across the width or height of that slurry stream, instead of only taking part of it and therefore only accounting part of the heterogeneity. Finally, a Vezin type of sampler can be used to again sample the full width and breadth of a slurry stream, or fines dry type of streams. Vezin samplers can also be used to fully represent the material stream flowing through it. So these 5 examples of one-dimensional sampling illustrates the design principles of sampling an entire process stream width and height with a single sample increment every time the sampler moves. So now that we know how to take a sample through one-dimensional variability, the equipment design that performs this function has to comply to certain rules. Now, the theory of sampling written by Piaget illustrates the risks of sample taking within the industry. Some of the rules, definitely not all of them listed here, is that the cutter gap must be larger than a minimum of 10 millimeters. However, at larger slurry flow rates, those cutter gaps need to increase, sometimes up to 70 millimeters. For dry sampling systems, the cutter gap is most often dictated by the particle size, where the rule then says that the cutter gap has to be 3 times the nominal particle diameter. There are also certain rules on cutter speed. For linear moving samplers, the cutter speed must be limited to 0.6 meters per second. For radial moving samplers that turns around a circumference, those tip speeds are typically limited to 0.45 meters per second. There are also rules about cutter geometry, shape, size, sharpness of cutters, etc. But for the current discussion, we can determine that a slow-moving cutter with a significant opening, traveling across a relatively large mining stream as we find in the gold industry, means that we will take a lot of sample increment. This is necessary because we do have to capture the variability that exists across the dimensions of the stream. So typically, for a slurry ranging from 500 to 5,000 cubic meters per hour, we would take a sample increment volume every time the sampler moves of between 2.3 to 70 liters. For a dry application with 50 millimeter particle top size, which means 150 millimeter cutter opening, if the flow rate runs between 100 and 1,000 tons per hour, we would respectively sample between 7 and 69 kilograms per increment. The remaining question is, now that we're left with one-dimensional variability along the length of the pipe or the conveyor, how often do we need to take a sample increment to produce a composite sample? Now, as a general rule of thumb, and like I mentioned, gold sampling can take us sometimes days to explain, it might be necessary to take as a heuristic a sample increment every 5 to 15 minutes to capture the process variability. Now, what does that mean? Well, on the bottom left-hand corner of this slide, we show the process variability of a typical gold operation Please note that this is not actual data, but fictional data to illustrate some of the principles of sampling. We can see by the red line that the grade on the y-axis changes quite significantly over time. Furthermore, we're going to use one typical sampler mechanical equipment to take samples of this gold feed stream. In the first sampling regime, we're using the sampler at 120-minute intervals. Now we know that this sampler is accurate because each extraction event is exactly on the red line of variability. So there should be no questions asked around the accuracy of the sample. In the second regime, we're going to use the exact same accurate sampler, but we're going to sample at intervals of every 15 minutes. Now, in the first regime of 120-minute sample increment intervals, we may end up with a gold grade of 0.58 because we unfortunately coincidentally only sample the stream when the grades are very low or very high. If we sample every 15 minutes, however, that sampling regime will capture the variability of the flow stream in terms of grade as it goes from the maxima all the way down to the minimum grades. So by using the same sampler, an accurate one, but changing the sampling regime in terms of how often it takes a sample cut, we could change our effective sampling result, and this is called sampling precision. So to tabulate the results from the previous slide, for slurry sampling at 500 cubic meters per hour, we'll typically end up with 2.3 liters of sample increment. If we go up to 5,000 cubic meters per hour, we'll typically end up with 70 liters of sample increment. If we take a sample increment every 5 minutes, in other words, 12 times per hour, over an 8-hour shift, we would produce 221 liters of primary sample increment. So it very quickly becomes evident that some form of secondary sampling or sample preparation would be needed to subsample that 221 liters into an ergonomic sample that is suitable for laboratory analysis. Similarly, for 5,000 cubes an hour, we'll end up with just over 6,000 liters of slurry sample. If we relax the sampling interval to 15 minutes, maybe because your particular gold is less variable, we'll still end up with 74 and just over 2,000 liters of primary sample increment over an 8-hour shift. And even then, some form of secondary or even tertiary sampling may be required. For dry sampling systems, we could end up anywhere between 224 kilograms and 6.6 tons. And before we can subsample coarse dry material, it would be necessary to crush that material before secondary and tertiary sampling. Now, why is that? Pierre G, throughout his life, produced the fundamental error equation of sampling, listed here. Now, there are a lot of parameters in this equation that has to be determined through heterogeneity tests for all specific properties. These properties will be different from one gold mine to the next, and might even be different where you have a common processing plant being fed by multiple shafts. These properties might even be different for the multiple shafts feeding one plant, even though they are only a couple of kilometers apart. So once these parameters are determined, they can be grouped into what is known as a sampling constant. Our focus, however, is only on the highlighted parts today, which is the square of the standard deviation of the fundamental error. We use the square because it doesn't really matter if we're over or under accounting gold, so the absolute value doesn't matter. A sampling error is still a sampling error. The next term we look at is our sample mass, and we can see that the standard deviation of the fundamental error is inversely proportional to the sample mass. In other words, if you take more sample, whether it be larger sample increments, more often to produce a larger composite sample, your overall sampling error would be less. The next important parameter is the nominal top size of the particle nugget or cluster. We can already determine that if we're dealing with nuggets, the average particle size is not the determining factor, but rather the nugget that occurs within a coarse gold deposit. Now, what is particularly interesting about the particle size nugget or cluster parameter is that it is to the power of 3. In other words, if we manage to reduce our particle size from 10 millimeters to 5 by a factor 2, our sampling precision would improve by a factor of 8. So somewhere within the equation, there must be a minimum sample mass required, given a certain material properties with a sampling constant and a certain particle size to achieve a certain precision level for our sampling output. The question is, how much sample do we need? Ideally, the heterogeneity tests should be conducted to unlock the full potential of the fundamental sampling error equation. But as a general heuristic, this graph serves quite a bit of purpose in the practical world. What we have listed here is on the x-axis, we've got gold grade running from 0 to 1,000 parts per billion. On the y-axis, we have the composite sample mass in kilograms. We also have lines for fine gold and coarse gold. But before we look at the difference between fine and coarse, we can see that if gold grades are low, we typically need much more sample mass, according to this graph. When the gold grades are higher at 1,000 parts per billion, we could only use about 1.8 kilograms of composite sample. However, when the gold grades are low for fine gold, we would need around 18 kilograms of sample on this logarithmic chart. Now that makes sense because when your grade is higher, your variability generally is less. So the downward trend of this graph can be explained. Then when we compare fine gold to coarse gold, of course, the same trend would have to be followed for coarse gold, where higher grades means less variability. With coarse gold, however, one or two singular particles distributed within a body of ore could account for the entire grade. So if we deal with a room of fine gold within a certain enclosed volume, the fine gold would be more readily dispersed within that room to make up the gold of 1,000 parts per billion. If we're dealing with coarse gold and the same control volume, we might end up with just one or two particles, which means that for coarse gold, generally, there's much higher variability. Over to some pitfalls for dry sampling. Francis Pittard warns that because the largest fragments in blasted material run-of-mine stockpiles prior to the primary crushing at the plant are up to 25 centimeters or perhaps larger, it's absolutely impossible for anyone to collect a representative sample from such material. If we pause there and consider for a moment all the geological anomalies that can occur in a 250 millimeter lump of rock, it is quite vast. We could have inclusions, we could have nugget effects, we could even have gold nuggets themselves, gold metal nuggets within that rock. So the variability that occurs within that particle volume is huge. We would need tons of sample if we want to represent the actual gold grades within 25 centimeter large particles. He goes on to say, any attempt to do so is a loss of time and money and a very efficient way to confuse management with invalid data. Any type of sampling and any grab sampling in general is an exercise in futility. He concludes to say, from ignorance, this practice might continue, but it cannot and will not work, and it is the duty of management to eliminate this type of incompetence. Some general pitfalls then for slurry and dry gold sampling is that for a starting point, you can use the heuristic provided here. However, as soon as accurate samplers are installed, the heterogeneity tests should be conducted so that the fundamental error can be used to its full potential and the sample masses required can be calculated exactly. Gold is such a variable mineral and element that no ISO standard exists to sample gold. Frequent sampling increments are required to capture gold nugget effects or slugs of high-grade gold reporting into the process plant. Having an accurate sampler is only half the win, but the way that sampler is used in terms of its frequency is the other half of the sampling regime. The theory of sampling describes sampling errors and risks for all commodities, but as we already discussed, gold sampling is particularly challenging because of its variability and density, and special attention should be paid to the theory of sampling. Bias-generating devices are cheap, but lowest cost procurement does not lead to quality. Use only cross-stream samplers. Because gold is dense and segregates quickly, do not attempt to crush dry material too fine. Once the gold is liberated, it's almost impossible to keep the gold within your slurry flow stream or within your dry flow stream within your sampling plant, and not have it gravitate and fall through the sampling plant too quickly without subsequent samplers granting it the opportunity to be sampled. Combat gold segregation in slurry sampling by using technologies such as mechanically agitated hoppers. Do not try to sample coarse gold. The larger the particle is, the quicker it will settle. Rather, use a gravity gold recovery circuit, and the produce from there reports directly into the security-controlled gold room. Make sure that you control the security access to your gravity gold circuit and measure the produce and booleans resulting from the gravity gold circuit directly. Do not attempt to sample gravity gold. Sampling analysis with a typical industry standard of using 50-gram fire assay is often not sufficient. And again, the fundamental error equation of sampling can be applied to determine the minimum sample mass required for the necessary precision levels. A final note then about reconciliation. Mining sampling done by geology and plant metallurgical theory of sampling compliance sampling are two different disciplines with different methods. The only commonality between these two processing trees are the laboratory that does the final analysis on the sample. But because the fundamental tools and methods used to extract, prepare, and subdivide the samples to the laboratory are different, reconciliation between mine and plant is not likely from these two different disciplines. The new field of geometallurgy will answer a lot of questions about reconciliation. Run-of-mine sampling is costly. Sampling large particles with variability often results in a lot of sample mass and requires crushing and subdivision that results in expensive sampling plants. Therefore, slurry sampling has a much better opportunity of getting better sampling precision levels, but it comes with a responsibility to make sure that cross-stream samplers are procured, maintained, and operated correctly so that the samples are indeed accurate and reproducible. Thank you for your time.